Good morning. Finally, we get to the last topic of the class, the game theory, just elements of game theory, in particular the notion of two persons games, as you will see immediately today. And I think the class ends in a nice topic, in my opinion, and also an appropriate topic because it is not actually overly difficult. If you actually did your job and went through all the topics we learned so far, right now you're familiar with how you handle matrices. Um, you have some idea about probability theory. The pieces of game theory we'll cover in this class, in these last three remaining lectures, are not really difficult when it comes to, at least to going over problems. The computational aspect of it is again not that difficult. And I would say it's not overly difficult to understand either, again, provided you understand really well the previous topics, because right now you should have some ideas about probability and other things like that. One thing I want to say right off the bat before I move on, in game theory, the word game is kind of there because of default examples that illustrate what we call essentially human behavior in the conflict of interest situation. So don't think of a game, although the default examples are essentially actual games, like two people playing some games with some payoffs. In reality, of course, this applies to real life situations when it's not about games, but maybe about business interaction or any type of interaction where there is some sort of conflict of interest among the participants. So try to think of this word game in a larger context. That's my point I'm trying to make here, right? It's not, the point is not to spend some time doing math just to invent another game to play. And in fact, before I even define what a zero-sum game is between two players, let me give you just a basic example that should be kind of familiar to everybody, or to most people at least. When it comes to persons and conflict of interest, the players, so to speak, because we're going to talk about games in which we have two participants, they don't even have to be actual persons. I mean, only one can be a person that interacts with another entity that is in some sort of a conflict. Each time there is some sort of payoff in which one wins and one loses in that interaction, then you can think in terms of game theory. So for example, let's say you buy stocks in a stock market and you can either buy a long position. Basically, you buy a stock and you hope to sell it when the price increases, or you could have a short position when you basically borrow essentially a stock, you sell it immediately and then you hope the price drops so that you can profit from the decrease in the market price of that stock. So in that case, basically you can think in terms of some sort of opposite payoffs with whether the market is up or down, right? So if you have long position, market up, that's going to be a profit in this situation. If you have a short position and the market is up, you have a loss situation. So the movement of the market either gives you a profit or a loss depending on whether you have a long position or a short position. And the reverse is true, right? If the market is down and you are in a long position, assuming of course you actually liquidate that stock, you're forced to sell it, then you have a loss. And then if you have short position and the market is down, that's when you profit if you close that position. So the movement of the market is inverse with respect to, not inverse, it's going to give you a payoff or a loss depending on what type of position you make. So you could think of one player, you, having two options, either buying a long position or a short position, and market as another player if you want, although it's not a real entity, that's not a real human being, will have essentially a decision to be either up and down. That's just very simplistic way of putting it. I just wanted to point out that although in this chapter we're going to talk about two people meeting and playing a game, the motivation is really beyond that type of framework. So with that in mind, let's define what is a two-persons game. So basically, let's just write a quick definition. So a two-person game basically is the interaction between two people in competition, in which the decision of one of them may mean a loss or a win for the other one. So how do we illustrate this this type of interaction? So we're going to make actually use of matrices, and in particular we're going to talk about 2x2 matrices because we have this two-person game. For the most part, we're going to have also matrices larger than that, but as an example or two, but most examples are about two players with two choices essentially. So here's the default example of such a game, or such an interaction, conflicting interaction between two people. Let's say we have two guys, Bill and Joe, and each has, let's say each has two cards labeled A and B. And then each picks a card. Each of them picks a card independently. If the letters match, let's just say that Bill pays, and let's call Bill player 1 because later we're not going to use names. So Bill, call it player 1. So if the letters match, Bill pays $2 to Joe, also identified as player 2. This is just to make a decision how to arrange them in a matrix when we write these payoffs. If the letters don't match, then Joe pays, let's say, $3 to Bill. So for now, let's write the payoff matrix. Payoff matrix basically is the best way to arrange and illustrate what happens in this game, depending on the choices of Bill and Joe. Each of them has the same choices, right? To pick the letters A or B independently, and then if you can imagine them sitting face to each other with the cards face down, A and B, and then they just pick randomly one card, or not randomly, I mean they know which card they pick, and then they compare, and there are these two situations. If they match, one wins, one pays the other, and if they do not match, the reverse is true, right? The other person pays the first one $3. So to make a standardization of how you write these matrices, because we're going to arrange the choices by rows and columns. So let's write it down like this. So the choices for Bill and Joe will be given in the rows and columns of a 2x2 matrix. And the payoffs, that's very important. I'm going to underline this. The payoffs will be from the point of view of player 1, who will have the choices on each row. So player 1 plays the rows basically. I know it's kind of a lot to write, so you may want to pause to write this down and then follow up, because I want you to look closely when I go over the examples. So the payoff will be from the point of view of player 1, who by default will have the choices on each row. On each row, that's a singular. Nothing special about it, but just to standardize the whole thing, we'll assume that player 1 lists his choices by rows. So here's how that payoff matrix looks like. Let's say each of them has two cards to choose from, A and B. And once again, by column, these will be player 2 choices. And here, by row, over here, this will be player 1 choices. In this case, this guy is Bill, player 2 is Joe. Later we're not gonna give names, just we're gonna call it player 2, player 1. So a 2x2 matrix is a very natural way of writing this payoff. I hope it's clear for everybody, right? Because they interact, two players interact, and then one of them lists his choices by rows. So it's like whenever player 1 picks a card, it's like player 1 choosing either row 1 or row 2. Whenever player 2 chooses a card, it's like player 2 choosing either column 1 or column 2. So at the intersection of each row and column, you can write the actual payoff. And now pay attention here, because this is from the point of view of player 1, and because it's going to be either a loss or a win, we're going to use negative sign if it's a loss for player 1. So if the cards match, if player 1 chooses row 1, player 2 chooses column 1, if they match, we stated in the problem that player 1 pays $2 to Joe. So we're going to write -2, because from the point of view of player 1, that's going to be a loss of $2, which automatically is a gain for player 2. So in other words, any negative number is a win for player 2. Any positive number, any positive entry is a win for player 1. This is just by convention, because we could have switched this, but we have to make up our minds. So the same thing if they choose row 2, column 2. If the letters match, another possibility is B and B. Once again, Bill plays Joe $2, so it should be like a loss, -2. And if the cards are not the same, let's say the choice is A and B, then Joe pays player 1, so that means $3. And then again, if they choose B and A in that order, once again, player 2 pays $3 to player 1. So this is the payoff matrix, and the meaning is self-explanatory, I hope, right? It's the matrix that shows the payoffs depending on the choices the players make. Now, if you want to basically simulate what happens, let's say they play this game repeatedly, you can list, for example, the choices with each game, and then the tabulation of the winning or losses, right? So you have Bill, Joe, Bill, Joe. And let's say, for example, in the first instance of the game, Bill and Joe pick B and A. They do not match, so that means Bill gets $3 from Joe, so you can write $3 here and -3 from Joe. Okay, so the matrix doesn't contain both, right? Because once we know +3 for one player, that's automatically -3 for the other. Okay, that's why these are also called zero-sum games. Any win is a loss for the other and vice versa. Let's say on the next instance of the game, they choose letters A. That means Bill pays $2 to Joe. So we're going to take $2 from Bill and add it to Joe tabulation. Let's say they choose letters A and B. They're not the same. So again, I'm going to so if A and B, we're going to have, again, +3 to the Bill tabulation and -3 from Joe. And finally, let's say B and B. Let's put another example. If they match, then we're going to take $2 again from Bill and add it to Joe. So if they play the game 4 times like this, then we have, in the end, we have 6 - 4, $2 after 4 games. And surprise, surprise, -6 plus 4 is going to be -$2. Zero-sum game. So no matter how many times they play the game, whatever is the payoff at the end for one of them, that's going to be the opposite for the other one. We don't know which one loses in the end or not. It depends on the choices they make. We'll talk about that later. But whatever they end up with, that's going to be the opposite of the other guy. So I hope it's clear how we write these payoff matrices depending on the choices they make. And I want to put, before we move on to the second page, I want to write down another quick example. We can have any number of choices actually in a two-persons game. It doesn't have to be 2 by 2. So for example, let's say we play the same game with 3 cards labeled A, B, and C. So in that case, the payoff matrix, of course, will have three rows and 3 columns, right? And again, this is basically player 1, player 2 on the columns. If the letters match and there are now 3 possibilities, that's going to be a loss for player 1 of $2. A, B, B, C, C. In all other situations, when the letters do not match, obviously that's going to be a win for player 1. So you're going to put +3 in those cases. And in a two-persons game, you could have basically any type of payoff, right? It doesn't have to be only positive or only negatives. It could be, and I'm going to show you an example on the next page, it could very well be an interaction in which only one of them wins. The question is how much that person wins. So that's going to be obviously a biased game against one of the players. So stay tuned for what we're going to call, in fact, the least interesting example in the game theory, namely the strictly determined game. We need to know that case so that we can focus on the interesting case when it's not strictly determined. And you'll see immediately why that's not interesting. And I can anticipate a little bit by saying it's not interesting because the rational choice is obvious and there's no element of randomness in terms of what can happen in the long run if that game is played by 2 rational players. So stay tuned for the second page. All right, so let's analyze 2 examples that will lead us to the notion of a strictly determined game. Again, remember to pause and maybe rewind if you need to catch up a little bit. It's extremely important to really put yourself in the mind of the players, to really imagine that you actually do these interactions, because it's going to be much, much easier for you to understand the whole concept. So really make sure you imagine yourself that you actually are forced to play these games, and then you're forced essentially to make a rational decision in your interest. So here's an example to focus. We're going to have 2 examples kind of related, but let's start with the first one. Let's say the payoff matrix. So remember the choices, just like before, are A and B. And the payoffs are 3, 5, 2, and 1. And again, remember, we're not going to write this all the time, but remember the player 1 is the one that basically makes choices on the row. I mean, the choices on player 1 are listed on the row, and player 2 will basically choose the columns. All right, so look carefully at the payoff. So first of all, let's write a couple of remarks. Now, clearly, the game is biased toward player 1, like in favor of player 1, because no matter what choices the players make in this case, player 2 plays player 1, right? I mean, all the payoffs are positive. Remember, that means player 1 receives that payoff from player 2. So in this case, of course, if you're player 2, you're kind of poor you, because I mean, if you're forced to play this, you're gonna basically lose money no matter what. However, there are still some rational things to do in this case. If you look at player 1 wants to maximize his profit, obviously, right? So look at the entries 3, 5, and 2, 1. Obviously, so that's the first remark. Obviously, player 1 will always choose row 1. That's because no matter what player 2 chooses, and write this down and then look at the matrix carefully. So that's because no matter what player 2 chooses, player 1 will get a bigger payoff. So by choosing row 2, the player 1 will get $2, $1, but both of them are worse than choosing row 1. There is absolutely no reason for player 1 to not choose row 1. So no matter what player 2 will choose, it's in the interest of player 1 to always choose row 1, because that's going to give him the biggest payoff. But knowing this, and that's the key thing, knowing this, player 2 will always choose, and maybe pause a little bit and see if you understand what's the rational choice in that case for player 2. Okay, so pause for a moment and see if you can answer this. Okay, so knowing this, or assuming that player 1 has a rational behavior and that will choose row 1, player 2 will obviously choose column 1, because that choice will minimize the loss. The best player 2 can do is to minimize the loss. That's the only option for player 2. And because of this distribution of the payoffs, that is the only rational choice. Player 2 is not going to choose column 2, because that's going to be a larger loss, knowing that player 1 is not going to be stupid to choose row 2. So again, that's why the key word is going to be among rational players in the market, if you want, or in this conflict of interest. So player 1 will not be silly to choose row 2, and then therefore, if we believe that player 1 is not silly to make that choice, obviously player 2 can only choose column 1 to minimize the loss, knowing that player 1 will always choose row 1. So two rational players will always end up with that choice, A and A, which will give you $3 for player 1. This is called the value of the game. We're going to write down immediately the definition of that. But basically, when the trace is always clear, that payoff corresponding to that trace is called the value of the game. Now notice that how can I put it? So that so one of them is essentially responding to a rational decision of the other, of the opponent, right? So in this case, the player 1 was the first opponent for whom the decision is pretty obvious, row 1. And therefore player 2 would also rationally respond to that choice. But we can switch this and we can have a combination of payoffs in which the respondent is player 1, not player 2. So here's a quick modification of this example. So once again, we have A, B over here. And let's write down the payoffs slightly different, 3, 5, 2, and 6. If you look carefully here, the decision is pretty obvious for player 2. So basically the interaction, the analysis of the game starts by noticing that player 2 will always choose column 2. I'm sorry, will always choose column 1 to minimize his loss, because no matter what player 1 chooses, the amount to pay is lower, right? So I mean, in this case, the game is also still biased against player 2 because he still has to pay money. But if you look at the entries here, there's no reason for player number 2 to choose column 1. Absolutely no reason, because in that case he will pay either $5 or $6. But if he instead chooses column 1, no matter what player 1 will choose, he will pay less. $3 and $2, no matter which of these will end up, are far better than $5 and $6 to pay. Remember, the player 2 can only minimize his losses. But then we can flip the reasoning. Player 1, knowing this, will always choose row 1 to maximize the profit, the payoff. Same type of reasoning, except that in this case player 1 is the respondent to a rational player 2, basically. So I just wanted to point this out with these two examples, that it works both ways. I mean, it doesn't matter who is listed as having the choices on the column or having the choices on the rows. The idea is that in a situation like this, because of the way these payoffs are distributed and their amounts, there is always an obvious choice for one of them, which immediately implies an obvious response for the adversary, for the opponent. So again, this is another example of what we're going to call a strictly determined game. So the value of the game is again 3 in this case. And there is a very easy test to figure out when we have such a game. Because the entries should be in such a way distributed so that this choice is obvious. So let's write down the definition now. So a strictly determined game we're going to write that down as SD. So a strictly determined game is when the payoff matrix contains an entry that is the least entry, that is the smallest, let's put it like that. So that is the smallest on its row and the largest on its column. That entry is called the value of the game. And it corresponds to the rational choices of the players. Right, so in such a game, you always have a choice, basically. Both of them have the same choice. And so if you look carefully in these two examples, this entry 3 satisfies that property. If I look at, for example, at 1, let's look at the first example. Let's pay attention here to the first one. So if I look at 1, that's the smallest of its row because it's less than 2, but it is not the largest on its column. On the other hand, 3 is the smallest on its row because it's less than 5, but it's also the largest on its column because this 3 is greater than 2. So whenever you have an entry like this, the game is strictly determined, and that's going to be the value of the game, which corresponds to the rational choice. Same thing in example 2, 3 is less than 5 and greater than 2 at the same time, and that's going to be the value of the game. 5 doesn't satisfy that, or 2 doesn't satisfy that, right? Because 2, while it's less than 6, so 2 is the least on the row, is not the largest on the column. So you're gonna have, the homework is pretty short, it's pretty easy actually. So when you have this question, is the game strictly determined or not, you look at all entries and ask, do I have both of these conditions? Smallest on its row, largest on its column. And that's gonna be the value of the game. Now, my first example in this lecture, what was that? That was the, with the entries -2, 3, 3, -2. And we kind of feel that in that case, the choice is not obvious because no matter what you choose, you could either win or lose depending on what the other player chooses, right? So that's not going to be a clear choice. So you look at each entries, right? So what's the lowest on row 1? That's -2. That's the lowest on row 1. But -2 is not largest on column 1. What about the other -2 on the second row? That's the smallest on its row, but for sure it's not the largest on its column. So basically we do not have any element with these properties. Therefore, this one is not a strictly determined game. And so this is the interesting case, right? Interesting case, because there's not much to say on strictly determined games. If there is such interaction, two rational players will make a single choice and then that's the end of it. If it's not strictly determined, then the question is, if we play the game repeatedly, do we have a certain strategy? For example, imagine for instance that player 2, or let's say player 1, right, keeps on choosing row 1, keeps on choosing row 1, keeps on choosing row 1, and then let's say for a while player 2, chooses column 1 basically, right? So that's going to be a loss for him. But then later on, maybe player 2 says, well, player 1 is in the habit of choosing row 1 all the time. Maybe I'm going to choose column 2. And then if we still match with, row 2, column 2, then of course I'm going to win $2. And if that choice happens, then maybe player 1 will change his strategy and then starts to choose row 1, hoping that player 2 will still choose column 2, and so on and so forth. So then here comes the question, and that's going to be the motivation for the remaining questions. Can one of these players, can we choose the A and B, let's say, can we choose A and B according to some probability distribution? So as to maximize the overall payoff. I mean, shall I choose, for example, half of the time row 1 or row B? Shall I choose maybe 1/3 of the time row 1 or row B? And so on and so forth. That's where the probability theory comes into play. How do we choose, according to some probability distribution, how do we choose these cards, in this case, these choices A and B, so that in the long run, we maximize the profit? And each player will ask the same question. So therefore the question is there any probability distribution for both of them that will basically provide the best possible outcome for both players? So that's going to be the topic for the remaining two sections, and that's it for today. Thank you.